Hey there guys, welcome to Unit 6 Notes D. In this last section of Unit 6, we're going to take our stoichiometric calculations and we're going to use them to determine the reactant that's going to run out first, therefore limiting the reaction, and then how much product can be formed with a calculation called percent yield. So let's start with the limiting reactants. Dealing with chemicals, you may also hear this called a limiting reagent, same thing. The idea here is that one thing will run out and therefore stop the reaction from being able to continue to make product. So the first time we look at this, let's look at something that's not chemistry based. Let's look at just combining bolts, washers, and nails together to make maybe a picture hanging kit. The idea here is that we need to figure out what's going to limit the reaction. So in this example, I have 87 bolts, 110 washers, and 99 nails. Those would represent the amounts of reactants available for the reaction to proceed. In the end, we want to make one kit, one set, one compound of a bolt, 2 washers, and 1 nails. Think of these as the amount that need to go into the product. Now the question is, how much product can I make? And then what's going to limit me from being able to make more product? So the idea here is that you would consider each reactant individually as if it were the limiting reactant. So for example, if I have 87 bolts and unlimited washers and nails, since I only need 1 bolt, I could make 87 kits. On the next reactant, 110 washers, but I need 2 per kit. So that means I can only make 55 kits since I need 2 each. And that would assume that I have unlimited nails and bolts. If nails was my limiting factor and I had unlimited bolts and washers, since the kit only needs 1 nail, I could make 99 kits. Out of those 3 options, making 87 kits, 55 kits, or 99 kits, you're going to choose the least number, which would be the 55 kits. I can only make 55 kits because then I will have run out of washers. I cannot make a 56th kit, forget a 87th kit or a 99th kit. I'm out of washers. I have no more reactants to give. And so the most product I could make is the 55 kits. And that's because the washers limit me from being able to make more. That would make the washers, theoretically, this limiting reactant. Now let's look at this as with a chemistry example, considering all calculations need to be based on the limiting reactant. So first example, we're going to be looking for the mass of sulfur dioxide, which is going to be one of our products. And it's going to give me 2 amounts, carbon disulfide and oxygen. So I'm going to give you, to start off with, an unbalanced equation. We can see the carbon disulfide and the oxygen are my reactants. So in these questions, they're going to give you 2 amounts of reactants. That's the main thing that differentiates this calculation from the percent yield calculation. When you're starting off with 2 reactants, you have a limiting reactant problem. You've got to figure out which reactant runs out first. The question here is asking what amount of the sulfur dioxide will be formed, how much of our product will form. So the first thing we have to figure out is whether we're basing that off the CS2 or the O2, and then we can give the correct answer. All of these are stoichiometric calculations. So what's the very first thing that you need to do for stoichiometric conversion? Well, you have to balance the equation. If you're doing stoichiometry, you need the mole ratio. And where do those numbers come from? Our coefficients. So the first thing we need to figure out is the coefficients for this equation. Is this equation balanced as is? No, it's not. So let's go ahead and balance that equation with the 3 and the 2. Now that I have this balanced equation, I can proceed with the problem. This is giving me the relative amounts. I have 1 molecule of CS2 per 3 molecules of O2 required to make 1 molecule of carbon dioxide and 2 molecules of the sulfur dioxide. So this is our relative amounts. It's going to give us our mole ratios when we get into the math. So let's go ahead and start our math. Where should we start? Usually you would start with the given. The problem here is you have 2 givens. The truth is, it doesn't matter which one of those you choose, because you're actually going to have to convert both of those to the sulfur dioxide so that you can figure out which one runs out first. So I'm just going to start with the first one they gave us, which is the 95.6 grams of carbon disulfide. So I'm going to write that as my given. Over 1. But the difference with stoichiometry is you can't just use gram or mole. You also have to say of what, because notice how we have all these different substances involved. So it's the carbon disulfide, or CS2, that I'm starting with. That entire unit, gram and the substance, is going to go into the denominator of my next conversion factor. The very first thing I would want to convert to is moles. When you change the unit itself, gram to mole, you have to keep the substance the same, CS2. I know I want to keep converting into something else, so I'm going to go ahead and bring my mole of CS2 to the bottom. Now here's where everybody gets stuck. Now that I've got to moles of CS2, what is it that I want to find next? So you've got to look at what the question is asking for. The maximum mass of sulfur dioxide, this guy. So that's going to tell me what substance I want to change into, SO2. But because I've changed the substance, I have to stay in moles. You can only convert one part of the unit at a time. So you have to go from mole to mole when you change the substance. The question does ask for mass, however. So I'm going to bring my mole of SO2 to the bottom and put my mass, or grams, of SO2 on the top. So it's going to set up going from gram to mole, changing the substance, and then converting out of moles back into grams. The goal is to turn the reactant that I'm starting with into the product that it's asking for. So now let's start plugging into the numbers. Always start with your mole ratio. Once you identify your mole ratio, you know the one and only place that the mole will not be equal to 1. Outside of the mole ratio, you always have 1 mole. The mole ratio numbers come from the balanced equation. So what mole should go on top for SO2? The balanced equation shows that there's 2 moles of SO2. For CS2, there's no coefficient, which we would assume means there's 1 mole of CS2. So the mole ratio numbers come from the balanced equation. Outside of the mole ratio, we're going to need to calculate for grams. So what conversion factor was it in grams that was equal to 1 mole? Here's where I want to plug in my molar mass. So I'm going to take my mass of carbon, 12.01, and I'm going to add the mass of sulfur, which is 32.07 twice. And I want to plug that in for the molar mass of CS2. And then for SO2, here I'm going to have the 32 once, but oxygen, which is 16 twice my molar mass of SO2. And plug that in for the grams of SO2. So let's go ahead and get that far in our calculation. Starting with 95.6 grams of CS2, divide by the molar mass, multiply by 2, and then divide by the molar mass this time, multiply this time by the molar mass of SO2. And see what that gives me for the amount of SO2 that would be formed based on carbon disulfide. So far, starting with our carbon disulfide, if I convert this to grams of SO2, I get 161 grams. The molar mass of CS2 turned out to be 76.2, and for the SO2, 64.1 grams. Now, we want to convert the same way, but this time, I have to start with a different given. I have to start with my new given of 100 grams of oxygen. I'm literally going to do the exact same thing, but this time starting with 100 grams of oxygen instead. And notice the decimal after the 100 to give this 3 significant figures. Grams of O2 instead. So now since I'm starting with grams of O2, I'm going to put that in the denominator. Grams of O2. And just like last time, the first thing I want to do is convert to moles. Moles of O2. When you change your unit, you have to keep the substance the same. So now let's go ahead and put our moles of O2 on the bottom. And the next step is going to be to convert to the type of product. So again, you can come back here and see we're looking for mass of sulfur dioxide and realize we want to change to sulfur dioxide. When you change the substance, you're going to keep the moles the same. We changed from O2 to SO2, so we're gonna have to go mole to mole. It's the only way we can change the substance. Now I wanna go ahead and put the mole of SO2 on the bottom and convert to the grams of SO2, since I am looking for mass. So now we want to plug in our numbers, and just like last time, I'll start with the mole ratio here. Just like last time, for SO2, I've got 2 moles. But how much O2? This is going to be different because we have a different reactant, right? So we've got to find the O2, and the coefficient here is 3. So that's going to produce quite a different answer. On top of that, we're going to have a different molar mass since we're starting with oxygen. So first, let's plug in our 1 mole. Now the molar mass of oxygen would be 16 twice. And then SO2, we had already found. No need to find it again. Plug in our molar mass of the SO2. So now I want to take my 100 grams of oxygen, divide it by oxygen's molar mass, use our mole ratio, so times 2 divided by 3, and then multiply by the molar mass of SO2. And that should give me my grams of SO2, but instead of basing it on CS2, it's going to be basing it on O2. So let's go ahead and type that in. So based on oxygen, I would be able to make 134 grams of SO2 using the molar mass of 32 even for O2 and the 61.4 again for the carbon disulfide. So based on CS2 with unlimited oxygen, you can make 161 grams. Based on oxygen with unlimited carbon disulfide, I can make 134 grams. These are my 2 options. This is just like being able to make 87 kits, 55 kits, or 99 kits. Here I can make either 161 grams or 134 grams. Which one is it? Can't be both. Which amount of product would be correct? The idea here is it would be the lowest one, 134 grams. And that's because once I've made 134 grams, I'm out of oxygen. Can I make SO2 if there's no O? Of course not. I have to have oxygen in order to make sulfur dioxide. So if I'm out of O, I'm done making product. So I'm done, dead in the water at 134 grams. I can't make 135 grams, 136 grams, forget 161 grams. Can't happen. I'm done at 134 grams. That is the maximum mass I can form, is the 134 grams. There are 3 questions that could really be asked on this. What is the limiting reactant? In which case, you would name the reactant that produced your least mass. Less common, they might ask you what's the extra stuff or what is in excess. So the idea here is that if you run out of oxygen, you will have leftover CS2. So the fancy term for that is excess. And then what this question actually asked would be our 3rd one. What is the mass? And they like to say what's the maximum mass too, to kind of throw you off and try to make you pick the big one. But the maximum mass you could form would be the lowest amount because you're out of stuff to build with, right? So these are the 3 types of questions they could ask you based on this. Regardless of the type of question, you're always going to have to start with each reactant and convert it to product. You pick your lowest one. If it asks for mass, you give the mass. If it asks for limiting reactant, you name what started that calculation. And if it asks for excess, it's the other guy. All right, let's move on to something called percent yield. Now that we know how to choose which reactant will run out first, I'm going to be interested in how much product I make. So in a percent yield calculation, we're going to compare how much product we should have gotten to how much product we actually got, because all labs have sources of error. So even though you think you're supposed to get 100 grams of product, maybe you only get 80 grams of product. That would be an 80% yield. How much product is actually obtained? And so the percentage actually would just take the yield that you actually got in the lab and divide that by the amount you calculated through stoichiometry that you were supposed to get. And then percentages, of course, are times 100. And remember, all percentages should be rounded to the 10th place. All right, So as we calculate the percentages, as we calculate the masses, as we just determined, oh, we're supposed to get 134 grams. That was all theoretical. That was based on 100% perfect lab, which we know never happens. That's called the theoretical yield. What really happens is called the actual yield. I actually call this the lab yield sometimes. So whatever you actually get in the lab, you're going to then compare to your theoretical yield. The theoretical yield is always calculated. The question will never give you the theoretical yield. The question will have to give you the actual yield, or you would be actually doing it from an experiment. So usually what they'll do is they'll give you the amount of reactant for you to convert into product for yourself, and then tell you how much product was actually formed. So let's look at an example here. Let me go ahead and put up the balanced equation. So the first thing that I want to do is point out kind of the elephant with this question. Why are we repeating so many C's and O's? Why didn't they just combine this stuff? This is what it looks like in organic chemistry. And so this is just something that we've kind of got to get used to. We've got to be able to count how many total C's and how many total O's and be able to compare them. And then when we do get to our organic chemistry unit, we can actually learn that this is very informative, much more so than combining them, in terms of us being able to understand what structure is in the organic compound. So for right now, we're just going to work with it, and then when we get to Unit 14, we'll actually see how this plays out. So my first question here, before we get back to the math, is this balanced? Can you deal with these C's and H's and O's all spread out like this and figure out if there are the same amount on each side? So what do we think? Balanced or not balanced? It is balanced. Whew, yes, balanced equation. So no coefficients we have to deal with. We are going to still be using a mole ratio, so that's helpful, 1-to-1. All right, let's look at what we got in the question. It says we start with a 10-gram sample of this C2H5OH. So what I like to do is actually put the numbers on the equation so I can keep track of whether I'm being given reactants or products. So I'm going to go ahead and do that. 10 grams of the C2H5OH. The next number it gives me is the 14.8 grams, and it's this big choo-choo molecule that ends with C2H5. So that would be this guy. Tells me I make 14.8 grams. Okay. If you do this and both of the numbers that they give you are on the reactant side, you have a limiting reactant problem like the one we just did. But if you do this and you have a number on the reactant side and the product side, then you know you have a percent yield question. Our goal is going to be to take the reactant and turn it into this product and figure out how much we should get in theory. This conversion of 10, let me use my sig figs, 10.0 grams of the C2H5OH into some number of grams of this big old guy, CH3COOC2H5. That's going to give me my theoretical yield. How much would this reactant actually produce? Then we're going to compare that to how much actually was made. The reactant always gets converted into a theoretical product, but the product given is always just simply the actual yield. So if it tells you how much you got in the lab, that would be your actual yield. The only other way you might see this is if you were actually doing an experiment and determined how much product you got, then you could calculate how much you should have gotten and compared your answer to that. Pretty similar to a percent error, just kind of the opposite. Looking at how much we really made as opposed to how much we lost. All right, let's start this math. First thing I want to determine is my theoretical yield. And to do that, remember, we were going to take our 10 grams of reactant and turn that into the amount of product. So I would start with my 10 grams, 10.0 grams of C2H5OH, put that over 1. Gram of my reactant will go on the bottom. So grams C2H5OH. And then the first thing I would do, always convert it into moles. And when I do that, I'm going to keep the substance the same. Now, I want to convert to product. So as I convert from one substance to the other substance, we're going to put the moles that we were leaving off with on the bottom, the C2H5OH, and I'm gonna turn it into the same product that they told me the actual amount of. It wouldn't do me any good to convert it into water because I wouldn't have any water grams to compare that to. So I'm gonna convert that into CH3COOC2H5. But when I change the substance, I stay in moles. We do want to convert it to grams so that we can compare it to these grams. So that's our third conversion factor there. Moles of the, running out of room here, CH3COOC2H5. And then I'll put grams of that same thing on top. All right, same thing we do. First, start with our mole ratio. The mole ratio is going to come from our balanced equation, which if we remember, this was already balanced, so the coefficients are all 1. So 1 to 1. Outside the mole ratio, the moles are always 1. 1 to 1. So then you've just got to figure out what to put for the grams for each substance, and then how to put this all in the calculator. So first, what is our molar mass of C2H5OH? Here. What is our molar mass of CH3COOC2H5? A lot of atoms to add up there. Make sure you get them all. Molar mass of that would go here. And then you want to divide by the C2H5OH molar mass and multiply by our big ol' ethyl acetate molar mass. So let's go ahead and get that all calculated out. What is our theoretical yield? So molar mass of the C2H5OH was about 46 grams, and of this big ethyl acetate was about 88 grams. So once we actually do that division and multiplication, we would get our final answer of 19.1 grams. So in theory, if 100% of those 10 grams of reactant was converted into this product, we would get 19.1 grams. But is the theory ever what happens in real life? Usually not. Usually there's some kind of source of error. There's something that stops this reaction from being 100% effective. As a matter of fact, instead of getting 19.1 grams, we only got 14.8 grams. So now our next job is to compare that 14.8 grams to the 19.1 grams. We want to find the percentage of how much stuff we got out of the whole thing we were supposed to get. So we're going to put our 14.8 on the top and our 19.1 on the bottom. So it looks something like this. So notice they called it experimental yield here. The idea is whatever you actually get from the experiment goes on top. So you got your 14.8 on top of your 19.1. And so we would get a percent yield of 77.5%. This is essentially the opposite of percent error. You want a high percent yield. You want to know that you're making most of what you were supposed to get. The worse your percent yield, the higher your percent error. They complement each other. You want to make a high amount of your product. You want to minimize the sources of error in your lab. So you want a high percent yield. All right, that concludes the notes on percent error and, not percent error, percent yield and the limiting reactant. So we're all done with Unit 6 now. The next set of notes that you're going to be looking for are for Unit 7. We're going to start gas laws. See you there.